Hey, Physics 20s, Mr. Jukla here to talk to you about a brand new lesson in a brand new unit. So if you don't already have your Unit 4 workbook out, now's the time to get it out. We're looking at lesson number 1 that is all about, that's not a felt pen yet, that is all about work. All right, so one of the first things that I want to give you here, something that we'll keep in mind throughout, well, this lesson as well as kind of the rest of the unit, is just a little bit of an idea of work. So work is very closely related to energy. That's like the title of this unit is work and energy. Work, actually, when I look at it in terms of a definition, is actually equal to a change in energy. So you might remember that triangle, the delta, capital delta, as a change in. So whenever I'm doing work on an object, I'm attempting to change the energy of that object. So work and energy go hand in hand. So just keep that in mind as we go through. Whenever we're doing work, we're trying to change the energy of an object. Now notice we're talking about a particular object. So work in real life is a little bit different than work in physics. So when we talk about work in physics, we're talking about a force moving an object. So a force moving an object. And we're talking about the work being done on that object. So what two things do we need in order to do work on an object? Well, we need to apply force to it, and it needs to do work on it. Classic example of this is this person is just working so hard, they're like sweating, there's drips of sweat coming up, puddles of sweat on the floor. They're working so hard trying to push whatever this red thing is. Maybe it's a wall, maybe it's a fridge, who cares? It's too heavy for them to move. The person, oh, absolutely. They're working hard in a fruitless effort, not moving that wall, not even a little bit. But they're working hard. But the wall itself, I'm not too concerned about the person necessarily. I'm concerned about the object, and in this case, the object is the wall. If the wall doesn't move a distance, it's got a force, so it's got that one. But if it doesn't move a distance, it doesn't do any work. And you probably remember this a little bit from science maybe 8 or so. Work is equal to force times distance. So again, if the distance is 0, then the work is 0. Or if the force is 0, then obviously the work is 0 as well. So you need a force and you need a distance. Cool. We're going to explore this formula quite a bit today, actually. Work is equal to force times distance. That's a big focus of today. First thing we'll look at is, well, what the heck is this? Work done by a force F is equal to that force times the distance. That's normal, but then times the cosine theta. Well, that's a little bit weird. Another important thing to note for this, work, just like energy, we measure in joules. And you probably remember that from previous courses, but we'll just put it out there to be nice and clear. So force is the magnitude of the force measured in newtons, just like we had last unit. Distance is the magnitude of the displacement, or d is the magnitude of the displacement, measured in meters, all standard units. And then theta is the angle between F and D. Now, when we think about this for a second, things really start to make sense. I need F, my force, and my distance in the same plane. In the same plane. And as of right now, I've got force going up at a crazy angle and distance completely horizontal. But if I need them to be in the same plane, well, then it starts to make sense why we're using cosine theta, right? Because realistically, what part of the force is in the exact same plane as the distance? Well, that's just force x, or the x component. And then I've also got my y component, which we're not really going to deal with too much here, but it's that x component that we're really looking at. And if I wanted that x component, well, I've got my hypotenuse. Let's highlight that in green. I've got my angle, and I'm looking for my adjacent side. Well, that sounds like cosine, the exact same things that we've been doing in Unit 1 and Unit 2. So FD cosine theta is a nice little shortcut for that, making sure everything's in the same plane. So a couple quick little examples to check out here. And this is really focusing on the whole cosine theta, where theta is between F and D. Just get that thing totally out of the way. Oh, I can minimize it. Ah, there we go. That's even better. Learning stuff, new stuff every day here. So the first one, I just say, okay, well, the work done by F, that's work is equal to force, that's 100 newtons, times the distance, well, that's just 5 meters, times the cosine of theta, well, it's the cosine of 40 degrees. And when we go ahead and plug all that stuff in, you go ahead and plug that in right now. I'd better put this on pause while I do this. And it turns out that that is 383 joules. And one thing that we'll note is that it actually came out as a positive. We'll talk about that more in a second here, but it did come out as a positive number. That's something important to note. The other one, okay, let's check out the second one. So I've got FD cosine theta for the blue block as well. My force is 700, my distance is 8 meters. That's not too bad. But if I wanted the angle between F and D, the angle's actually all the way over here, theta, which is equal to 150 degrees. So let's go ahead and plug that one in. So let's say work done by that force is equal to the force 700 newtons times the distance, which was 8 meters, times the cosine of 150 degrees. Again, you can put your video on pause. You can plug in your numbers here and see what you get. So I ended up, I'm not going to have sig digs for this, 850 joules, but something really important happened here. It came out as a negative number, right? A negative number. And we can already start to explain that, I think, right? Because remember when we said, I'm just going to do this off to the side, work is equal to a change in energy. Well, when I look at this first example up here, the force and the distance are in the exact same plane. So the force and the motion are in the same plane. So that force would be helping the motion, trying to speed it up almost if you want to look at a particular type of energy, kinetic energy. So helping the motion. So whenever it's helping the motion, we call it positive. The second example down below there, that force is the opposite direction, or at least part of it's the opposite direction to the distance, which means it would be trying to slow it down, right? If it's opposite to the motion, the force is trying to slow it down. So when we think about that change in energy, we're trying to take energy out of the system, which means it would be a negative change in energy. Oh yeah, okay, that's good. Now, honestly, the way that I look at this one, I typically don't use 150 degrees. I would throw this in and I'd say work is equal to force, so 700 newtons times the distance, so 8 meters times, let's see, the cosine of 30, and I'd say, oh, okay, well, that's just, 4,850 joules, but then I would recognize that they are in opposite direction, and I would throw the negative in. Right? So for me, that's a lot easier. You can work on this any way you want to, but for me, it's just easier to recognize, okay, opposite directions means it's going to be negative. Cool. Okay, so let's explore this a little bit more here. 3 cases you must know. Helping the motion, we kind of already talked about that. Resisting the motion, kind of already talked about that. Perpendicular to the motion, oh, we didn't talk about that at all. Let's check it out. So first and foremost, helping the motion. In this case, the applied force is literally the exact same direction as the motion. Same plane, every part of it's the same plane. So what's the angle here? 0 degrees. What's the cosine of 0 degrees? Well, that's just +1, right? So positive is kind of important. And if cosine theta is equal to 1, then realistically, we can cross that cosine theta off. We can put +1, and work done by that force is just the force times the distance. Hey, it's a grade 8 version of the formula. Nice, cool. Okay, the second one, okay, what's the angle between my force and my distance here? Well, if you're saying 180 degrees, yeah, you're absolutely. This one is truly the opposite direction. So the block is moving towards the right, but the person is clearly trying to slow it down, pushing directly towards the left. So what is the cosine of 180 degrees? Yeah, if you're saying -1, you are spot on. So again, we don't necessarily need to have cosine theta here. We can just say that that is, in fact, negative work. The person is clearly trying to slow that block down, clearly trying to take kinetic energy out of the system. The last one, what is the angle here? If Fn is perfectly perpendicular and the distance is perfectly horizontal, well, that's 90 degrees. What is the cosine of 90 degrees, you ask? Well, 0. And if cosine of 90 is 0, how much work is that force actually doing here? It's not doing any work whatsoever, right? So perpendicular force is no work whatsoever. So again, just a quick recap. If my applied force is in the same direction as my motion or my distance, I call it positive work. It's adding energy to the system. That's the top one. The middle one, if my applied force is the opposite direction to the motion, well, I'm going to call that negative work. It's trying to take energy out of the system. And if it's 90 degrees, that's the last one down there, no work's being done by that force whatsoever. There might be other forces doing work, but by this force, nothing at all. Cool. Some important notes. Work, just like every type of energy, is a scalar. Scalars, you probably remember, have no direction. So that means we cannot be using this east-west sort of reference system. That is junk. That's not for us. So what does the negative actually mean? The negative means, again, that we are trying to take energy out of the system, or that the change in energy is negative. The energy is going down in the system. Cool. The positive would mean you're adding energy. We kind of already talked about this one. Realistically, we just want the component of the force that is in the same plane as the distance, which is typically our x, which is why we're using f times the cosine of theta in order to figure out fx. So realistically, we're just looking at that f component, and that's why its work is equal to force times distance times the cosine of theta. There's the cosine, there's the force. It's realistically the x component. Cool. Another note with this is, and I've kind of already alluded to this a little bit, is, well, what if there's a whole bunch of forces acting on it? One force can do a certain amount of work, another force can do a certain amount of work. Well, we know that we can figure out like the net force just by adding up all the forces. The force plus the force of friction for this one, knowing that force of friction is in the negative direction. So I would say, okay, just throw a little negative in there. Cool. Very cool. So we can figure out the net force. Now, if I wanted the net work, that's the overall work that's being done, I can just say, oh, well, that's just the net force, times the distance. And that makes sense. The work done by a particular force is equal to that force times the distance. This is the work done by all of the forces. My net force, or sorry, my net work is equal to the net force times the distance. Cool. Another way that we could look at this is just sort of the definition of net work. So my net work is, well, it's what happens when I add up all the work that's being done. So that could be the work done by, let's see, force F plus the work done by force friction, but we'd keep in mind that the distance is towards the right, the force is towards the left, the friction force is towards the left, so I would definitely want to call that one negative. I'm even going to highlight that in a different color. Definitely call that one negative. Cool. So a couple different ways to look at that there. Let's jump into a quick example here and let's check it out. So we've got this sort of situation. If this box is moving right, so it is moving right, and it's moving at a constant 6.2 meters per second for 8.9 seconds, determine the work done by the two forces, F1 and F2. So let's think about this. Before we answer any of them, let's just think about this for a split second. What do I need in order to figure out the work done by force? I need that force, and I need the distance. Okay, I got force 1, so that makes A a little bit easier. Do I have the distance? Do not have the distance. So maybe before we even get into any of these, A or B, let's just find the distance, because that might be helpful for both A and B. Find distance. So it is uniform motion, the only kinematics formula that we really have for uniform motion. V is equal to d over t. I rearrange, d is equal to v times t. We plug in the numbers, 6.2 meters per second times 8.9 seconds. We see seconds cancel. That is just wonderful. Go ahead and take a moment to plug that in and tell me what you end up with. Perfect. If you're getting 55.18 meters, I think you're doing all right. So now let's look at part A. Part A is the work done by force 1. Okay, so this should be easy. The work done by force 1 is equal to force 1 times the distance times the cosine of theta. And I think we have all those things, so we can just go ahead and start plugging things in. So force 1 was 710 newtons times the distance, which we just figured out to be 55.18 meters, times the cosine of the angle, and the angle was, let's see, 25 degrees. Now when we plug all this stuff in, the work done by force 1, we're going to end up with a quite a big number here, I think. 35,507 joules. And you're probably thinking to yourself, those sig digs, that doesn't work out. Okay, let's do a slightly better answer. 3.55 times 10 to the power of 4 joules. There's still one thing missing from this. Let's go back up to the diagram and the question a little bit more. So it is moving towards the right. It means that the motion or the distance is this way. Is that F1 going to help that motion or try and take away from that motion? Definitely going to try and take it away. So what we want to make sure we do is we say, okay, well, this is definitely not positive work. It's trying to take energy out of the system. Let's call that negative work. And I'm highlighting that in red because it's just so dang important. So for part A, our best answer that we've got, the work done by force 1, negative 3.55 times 10 to the power of 4 joules. Or if you do it in kilojoules, 35.5 kilojoules, you're good to go as well. Nice. So that is part A. Part B, a little bit trickier with part B here. So we're looking for the work done by force 2. So we might be thinking to ourselves, and I'm probably going to erase this, so don't start writing this out. So we might be thinking to ourselves, I need to figure out force 2. And then we might be thinking to ourselves, okay, constant velocity, so that means in my x component, F net x is equal to 0, so that means F1x is equal to F2x, which is realistically just F2. So if I were to figure out F1x, I could figure out F2. I already know the distance. We could do work is equal to F2 times the distance. All right, that's absolutely one way that we could do that. So figure out the net force in the x, which is 0. And then we would go through and we'd say, okay, well, if it's 0, then F1x must have to be equal to F2x, just in the opposite direction. So then we solve that. That's definitely one way to do it. That's dealing with our net force in the x component. I think there's an easier way, though. Let's check this out, and it's our new definition. So what is the net work being done if the net force is equal to 0? And by the way, how do we know that the net force is equal to 0? Back up to the top, let's highlight in red. It's a constant velocity. What does constant velocity tell me about the forces? It tells me that they balance out, so the net force is equal to 0. So my net work is equal to 0. In my x component, what do I have? I've got my work done by force 1, and I've got my work done by force 2. And if those are the only two things, and they have to add up to 0, they have to be the same thing, but they have to be in the opposite direction. So work done by force 2 is just going to be equal to positive 3.55 times 10 to the power of 4 joules. I'd say that, well, it might be a little bit harder to reason our way through. Sure makes life an awful lot easier than trying to figure out net forces and everything like that. So again, two different ways to solve for B. Cool. Let's check out, I think I got 2 more examples for you. Oh, some space to work, more space to work. Okay, here we go. Similar sort of ideas here, but all of a sudden we're dealing with accelerated motion, it looks like. So we've got a 17 kilogram box, that's our mass, no problem, mass, is pulled to the right by a force F. Okay, cool. Yeah, got that. But due to 120 Newton friction force, so if the force is towards the right, it's moving towards the right, the friction force, that must be towards the left. We'll keep that in mind. It's accelerating left at 1.85 meters per second squared. It had an initial speed of 9 meters per second. We're looking for the work done by F to bring it to rest. There's a lot going on with this question. Holy mackerel, there's a lot going on. So first thing I might want to do is make a little free body diagram to summarize some of the ideas. So it's being pulled towards the right by a force F, and it's actually moving towards the right. Cool, so I even write that out down here. Its motion is towards the right. But it's got a friction force that's causing it to accelerate towards the left. So my friction force needs to be bigger than my force F, 120 newtons. Cool. So that means its acceleration, let's just add acceleration to this. Maybe I'll put it off to the side over here. Acceleration is 1.85 meters per second squared towards the left. So we got that one there. So this sort of sums up what's happening. There might be a person trying to push it to the right, but maybe they're not tough enough, so friction is slowing them down and they're eventually going to come to a rest. Cool. Okay, so we are looking for the work done by force F. So just kind of thinking this through, what do I need to figure out the work done by force F? Well, we need to figure out what force F is, and we need to figure out the distance. So both of those things are currently question marks. Okay, so we better figure out both of those things. Because it doesn't really matter what we're gonna do first. I got the free body diagram, so I guess we might as well deal with the force F first. So let's just say find that force F. So things that I know from last unit. I know that the net force is mass times acceleration, and I know that the net force is the sum of all the forces. So that's going to be my force F plus my force of friction, keeping in mind that if force of friction is towards the left, I might need to put a little negative in there. Cool, so let's expand this a little bit here. So F net, well, that's mass times acceleration, which is going to be equal to force F plus my force of friction. Okay, nice. So if I wanted to solve for force F, well, this is getting pretty simple. This is just like last unit. That's going to be my mass times acceleration minus my force of friction, still keeping in mind that force of friction is towards the left. Nice. So I think we actually have everything here. We can plug some numbers in, and we can solve for that force F. So let's see. It's a 17 kilogram block. So 17 kilograms times the acceleration. Now the acceleration is also towards the left, so what do we need to put in there? A negative sign. 1.85 meters per second squared. And then we're going to subtract from that my force of friction, which was negative 120 newtons. So go ahead, take a moment, plug that into your calculator, and let's see what we get for force F. We should, if everything checks out, get 88.55 newtons. 88.5. And with that, we can kind of think to ourselves, does it make sense? So back up to our diagram. One, is it in the positive direction? Totally, so that's good, just like force F should be. And then two, is it smaller than 120 newtons? It is, yeah. So two quick ways to double check. So the other thing that we need to do is we need to find the distance. So let's go through and let's figure this out. This is accelerated motion, right? So accelerated motion. It's good to make a variable list, pick a formula. It's all those kinematics things from units 1 and 2. So let's see. We've got VI is 9 meters per second, and that's in the positive direction if we're assuming that right is positive. So 9 meters per second. We also know VF. VF is 0, right? Because if it's coming to rest, that means VF must be equal to 0. I know my acceleration is negative 1.85 meters per second squared. Again, negative because it's towards the left. And then the distance is a question mark. So take a moment to pick an appropriate formula. get out your data sheet. And if you picked, let's see, VF squared equals VI squared plus 2AD, I think you're doing A-okay with that, right? Because what's the thing that's noticeably missing from our list? There is no time, so we want to make sure we pick a formula, well, that doesn't have time. So when I go through and I rearrange this, better grab a little bit more space here. When I rearrange this, distance must be equal to VF squared minus VI squared over 2A. So VF squared minus VI squared over 2A. And I'm hoping that people are getting better and better with the rearranging here, and you understand how exactly we got to this place. By this point in the course, you should be pretty good with that. If you're not, you'll probably want to ask some questions, whether it's me or somebody else, but you'll want to figure that out. Cool, so I'll plug in some numbers. Distance is equal to, oh, that's nice, 0 squared minus 9 meters per second squared over 2 times, that should be an A, over 2 times the acceleration, negative 1 point, I'm screwing up like crazy here right towards the end of the lesson, 1.85 meters per second squared. And again, that's a negative. So go ahead, put it on pause, figure out the distance. If you got 21.89, you are good to go. Awesome. And then finally, our very, very, very last step. Let's just cut this all off. So we figured out the force, we figured out the distance. Holy mackerel, there's only one step, and I would argue it's probably the easiest step. The work done by that force F is equal to the force times the distance. So that was 88.5 newtons times the distance, 21.89 meters. And when you plug everything in, we end up with 1.94 times 10 to the power of 3 joules. Actually, in your calculator, you could have got 1,938.53, but we'll take that one step further and include some significant digits. Wow, cool. So that is same idea, but now with a bit of accelerated motion. So what was the big idea there? What 2 things do we need to figure out the work done by a force? We need to know that force, and we need to know the distance. That's the big idea there. Okay, that's some space for me to work, more space for me to work, more space for me to work. Okay, last thing to really talk about here is the work done by a changing force. First, let's consider this. This is a graph. I've got a force versus a distance graph. It's a constant force, and we know that work is equal to a constant force times a distance. If I look at this graph, realistically, I've got the force from there to there. I've got my distance from there to there. That's like a length, and that's like a width. I don't know, we could call them that one. So on this graph, the work done is equal to the length times width, which is equal to the area realistically. So long story short, the big thing that you need to know, the work done on a force, or sorry, a force versus distance graph, the work done is the area under the graph. And what I mean by under the graph is between your actual line and your x-axis. So right there, so the area. Perfect, and that's about as hard as this last little bit gets. There is, like this is a little bit of a trick with it. So if I had a, obviously the distance here is going to be positive. Let's get a different color there. Distance is going to be positive. So if I had a positive force with a positive distance, that means this is going to be positive work. If I had a negative force, so maybe do that one in black, negative force with a positive distance, those are opposite directions. This one is going to be a negative work, right? So the area underneath. Now, how do you calculate the area of a triangle? 1/2 base times height. What about a rectangle? Length times width. Nice. And again, what I mean by the area under the graph is if this is my x-axis, under the graph in quotation marks there, I mean between my line and the x-axis. And same thing with over here. I don't know if this red's going to show up. Not really super great. I'll use blue instead. So between my line, so my graph, and the x-axis. So there's my area there. Sweet. So we've got this graph. This is our very, very last example. Determine the work done. And it's actually super easy. So I'm gonna get you to get started on this. But the total work done, some things that we need to note. First and foremost, the force is on our y-axis like normal, except it's times 10 to the power 3. What that means is each of these numbers is times 10 to the power 3. So that's 7 times 10 to the power 3. That's 6 times 10 to the power 3, and so on and so on and so on. The other thing to note is we've got centimeters over here. Ooh, centimeters. So realistically, when I'm dealing with this, this is not 1, this is 0.01 meters. 0.02 meters, and so on and so on. Because when we're doing our work is equal to force times distance, we want things in newtons and we want things in meters. Okay, last thing to note before I say go ahead and get started is this is kind of a weird shape over all 9 centimeters. Anybody see how we can make it into more recognizable, easier to deal with shapes? People are saying, oh, let's split it up here. Maybe I'll say this is area 1, that's a triangle. We can deal with triangles. And this is area 2, that's a rectangle. Even easier, we can deal with rectangles. And if I want the total area, we just add area 1 to area 2. So the work done is equal to the area total, which is equal to area 1 plus area 2. So I'm going to get you to put it on pause now. I'm going to do the same thing. We'll solve and we'll compare notes. Alrighty, so hopefully you had the opportunity to put this on pause and try it out for yourself. So again, we broke it apart into true, more distinguishable shapes. So a triangle and a rectangle. I figured out the area of the triangle up here turns out to be 1/2 base times height. So 1/2 times 0.09 times 4.5 times 10 to the power of 3. Notice the 4.5 times 10 to the power of 3 is from 2 up to 6.5. It is only this section here, not all the way from the origin. So that's 202.5 joules. The second part, the rectangle, I would argue is super easy. So what I randomly called the length was 2 times 10 to the power of 3 newtons. That's my force. Times my width, 0.09 meters, 180 joules. I want the total work. Easy peasy. I just add them together, 383 joules. So Physics 20s, that is it for our very, very first lesson of Unit 4. Excellent work. Talk to you again soon, everybody. Bye for now.